Hi, in this video I'm going to keep working on problem 8, but I'm going to answer question B, which is calculate the same forecast for this problem of cars, demands for cars along 6 years, but using a simple exponential smoothing forecast. So it's a different forecasting technique, and I'm going to solve only one of these problems so you can see how it works using a different forecasting technique. And I'm going to find the forecast error measurements in this case, okay? So if you take a look at page 34 of our class notes, demand forecasting, we have this question of what's the forecast using a simple exponential smoothing. I'm going to use alpha equal to 4, so let me go to Excel. And let me give you some extra space here so I can put information about our coefficient. So our coefficient is equal, let's use 0.04, that's one of them. I'm not going to do the 0.1, so I'm going to do only the problem with the coefficient alpha equal, what's coefficient, alpha coefficient equal to 0.4. And starting value, remember, for exponential smoothing we need a starting value, so our starting value is going to be 10,000 as given in the problem. So 10,000 is our starting value, our alpha coefficient is 0.4. So let's do we need a forecast for year 7. Okay, but to compute the forecast for year 7, we need this starting value of 10,000, and then all other forecast, or the forecast for the other years, is going to be equal to the previous forecast, which is 10,000, plus 0.04, which is our alpha coefficient, multiplied by the error. The error is the difference between the demand and forecast. I'm going to click on this empty cell, because in this empty cell I'm going to compute the error. Okay, so this will be the forecast for year 2. So what's the error? Let's compute the error here. The error is going to be equal to the demand minus the forecast. Okay, and then I have the true forecast for year 2. Okay, and then let's copy cells, the formula to all other cells. Let's compute the error for all other cells. So this, let me make it like centralized. Okay, so what's the problem after we move from here to year 3 is that we have to lock the alpha coefficient, because as we move the formula it keep moving this cell to other cells. So I have to lock cell H2. So I click on top, I go to the formula here and click on top of H2, which is our cell, and then press F4. Now it's locked. Now I can copy the formula to all other cells, and just to make sure that it is using the correct cells. So for year 7, what we have is the forecast for year 6 plus the multiplication of our coefficient and the error between the demand and forecast in year 6. So this is how you compute the forecast and errors using the simple exponential smoothing, okay, using an alpha coefficient of 0.4. Now let's compute the errors. So we have the error square, and I'm gonna do that quicker. We have the absolute deviation. We have the deviation. The absolute deviation, and then we have our errors. Okay, So to replicate the same problem as we had before, we have the errors already, but remember we are comparing the problem, asks what is the mean absolute deviation for years 4, 5, and 6 using the exponential smoothing. And then what we have to do is we have to compute the error square for years 4, 5, and 6. So the error square is going to be equal to the error multiplied by itself for each one of these years. And the deviation, which is equal to the error. Remember, the deviation and error is the same thing. The absolute deviation is the absolute value of the deviation. Okay? And why we are doing only years 4, 5, and 6? Because in the previous video, in the video before, we did the forecast and forecast errors for using a three-year moving average, simple moving average for 3 years. And now we want to compare if this mean absolute deviation using the exponential smoothing is smaller than the mean absolute deviation using the other techniques. So we are comparing techniques. This is what the problem 8 is about. We're using different forecasting techniques and using the errors and the errors measurement to make a decision which model is better. Okay, so this is the reason we are doing everything again and using the same data points, which is years 4, 5, and 6. Okay, so the mean error is equal to the average of the errors for years 4, 5, and 6. The mean square error is the average for the error square for years 4, 5, and 6. The mean absolute deviation is the same thing, but for the absolute deviation years 4, 5, and 6. The mean absolute percent error, just let me take a look here, is equal to the mean absolute deviation divided by the average demand for years 4, 5, and 6. And then the tracking signal, which is equal to the sum of errors for years 4, 5, and 6 divided by the mean absolute deviation, which is also -3. Okay. So these are the numbers, and what the problem is really asking is what is the forecast for year 7, and the forecast for year 7 is 8,599. And if you take a look at the solution on page 34, the third row, which is exponential smoothing using alpha coefficient of 0.4, the forecast is 8,599. And the mean absolute deviation is 1,207 units, the same thing that we have in the solution in our class notes. Okay, if we compare with the previous forecast, let me open here, and we can compare. So the mean absolute deviation for this case of using the simple moving average is 1,238 units. Which gives us a mean absolute percent error of 0.14. This one is smaller, is 1,207 units, and the mean absolute percent error is 0.1394. So using exponential smoothing with an alpha coefficient of 0.4, it's better than using a simple moving average of three periods. Okay. So this is how you use the different forecasting techniques and use the errors to compare these different techniques and see which one gets forecast values that are closer to the demand. Okay, I'm not going to solve the other two problems, the other two questions in problem 8, which is do the forecast demand using a simple exponential smoothing with alpha coefficient of 0.1. I'm not going to do this one. I will let you do it. And also question C, which asks to calculate the weighted moving average with different weights. I'm not going to do that. So I provoke you to work on your own and see if you can match those numbers that we have in the solution. But this is how you do it, how you get the mean, the measurement errors, and then you can make a decision which model is better. Okay.